and special procedures may be required. Five-minute point. Engine manufacturers' limitations restrict the use of takeoff power to a maximum duration of 5 minutes prior to making a reduction. Runway limited takeoff weight may need to be reduced to ensure that acceleration to VFTO and retraction of flaps within or at the 5-minute limit is achieved. This can sometimes be avoided by lowering the engine out acceleration height. VMCG, the minimum control speed on the ground during the takeoff run at which it is possible to regain and maintain directional control using the primary flight controls without the use of nose wheel steering after a sudden failure of the critical engine. The quoted VMCG apply in the flat-rated region and at zero crosswind. It will be lower at higher altitude or temperature due to a reduction in the engine thrust. VMCG increases by 5 knots per 10 knots of crosswind component. VMCA, the minimum control speed in the air, is the lowest speed at which it is possible to regain or maintain straight flight after an engine failure without exceeding any of the force, bank, or heading limits specified in the requirements. A bank angle of 5 degrees is allowed to control the aircraft's flight path. V1, takeoff decision speed, is the speed calculated for each takeoff, which defines the point beyond which the takeoff will be continued if an engine failure is recognized and before which takeoff will be abandoned. V1 must be equal or less than VR. V1 must not be less than VMCG. VR. Rotation speed is the speed at which the pilot initiates a change in the attitude of the aircraft with the intention of leaving the ground. VR varies directly with weight. VR must not be less than 1.05 VMCA, ensuring the aircraft can be controlled once airborne in the event of an engine failure. V2, takeoff safety speed, is the minimum initial climb-out speed from a height of about 35 feet with one engine inoperative. The speed provides a safe margin above the stalling speed and above VMCA. VFTO is the final takeoff speed. It is the speed at the end of the takeoff path in the fourth segment. It is used as a reference point to determine some approach speeds. It is used on a GA in the same way that it is used on takeoff. VFTO is never less than 1.25 times the flaps up stalling speed. VER, en route climb speed, is the speed that the aircraft is flown following an engine failure. If the climb has to be extended beyond the takeoff flight path, it gives the best climb gradient or best drift down after engine failure. At altitudes for approach and landing, VER is approximately 10 knots more than VFTO. For a missed approach, VER is used in the same way as it used on takeoff. Tire speed and brake energy limits. The calculation for the allowable takeoff weight assumes the aircraft is fitted with 190 mile per hour tires. The brake energy limits may be a limiting factor if a rejected takeoff is performed, and this too has to be included in the calculation of allowable takeoff weight. A runway is considered wet when the surface is covered with water not exceeding 3 millimeters depth, or there is sufficient moisture to cause the surface to be reflective, but without significant areas of standing water. A runway is considered contaminated when more than 25% of the required runway surface area are covered by standing water of more than 3 millimeters, 0.125 inches. If the water equivalent depth, WED, of slush, wet snow, or snow is above 3 millimeters, a runway is also considered contaminated. In other words, if the layer of contaminant would melt to water and the resulting layer would be above 3 millimeters, the runway is contaminated. For each contaminant type and depth, there is an associated precipitation drag consisting of landing gear displacement drag plus spray impingement drag. A certain water depth that results at the same precipitation drag exists for each contaminant. This is called equivalent water depth, WED. The WED is the contaminant depth multiplied by its specific gravity. A runway is also contaminated if it is covered by compacted snow or ice, irrespective of contaminant depth. Consider the braking action to be poor on ice or wet ice. Standing water is caused by heavy rainfall and/or inadequate drainage. Water has a density of 1 kilo per liter, 10 pounds per imperial gallon, with a specific gravity, Sg, of 1.0. Slush water is saturated with snow, which spatters when firmly stepped on. Slush forms as a result of melting snow at about plus 5 degrees and has a density of approximately 0.85 kilograms a liter, 8.5 pounds per imperial gallon, with a specific gravity of 0.85. Wet snow. If compacted by hand, wet snow sticks together and tends to form a snowball. Wet snow has a density of approximately 0.4 kilograms a liter, 4 pounds for an imperial gallon, with a specific gravity of 0.4. Dry snow, when loose, can be easily blown, and if compacted by hand will disintegrate upon release. Dry snow has a density of approximately 0.2 kilograms a liter, or 2 pounds for an imperial gallon, with a specific gravity of 0.2. Compacted snow is that which has been compressed into a solid mass, which resists further compression and holds together or breaks into lumps if picked up. Compacted snow is assumed to provide a breaking coefficient of 0.2 up to medium to good. A runway surface condition where braking action is expected to be very low is often due to the presence of wet ice. Wet ice is assumed to provide an aircraft wheel braking coefficient of 0.05 only. VGO, the minimum speed from which the aircraft can complete the takeoff within the available runway length after an engine failure. VGO must be above or equal to the minimum V1. V-stop, the maximum speed from which the aircraft can be brought to a standstill within the available accelerate stop distance, including stopway. V-stop must be above or equal to the minimum V1. Actual landing distance, ALD. This is the landing distance demonstrated in flight testing. It is the distance from a point 50 feet over the runway threshold to the point where the aircraft comes to a complete stop on a dry runway. Landing distance required, LDR. The dry landing distance required is the ALD factored by 1.67. For wet runways, this is further increased by 1.15, giving 1.92 times ALD. If the AFM contains approved contaminated runway performance, the landing distances are unfactored. In the FDH, the landing distances are always factored. On contaminated runways, it is the actual contaminated landing distance factored by 1.15 or the LDR wet, whichever is higher. Landing distance available, LDA. The LDA is the length of the runway which is officially declared to be both available and suitable for the ground landing run of an aircraft and capable of bearing the weight of the aircraft under prevailing operating conditions. The LDA normally commences at the runway threshold and in most cases corresponds to the physical length of the runway. However, the threshold may be displaced due to obstructions in the approach path. Landing threshold. The landing threshold is the point on a runway from which the LDA is measured. Maximum certified landing weight. This is the maximum structural weight certified in the AFM at which a landing, other than an emergency, is permitted prior to performance considerations. As the Avro RJ is not fitted with a fuel dump system, the AFM covers landing weights in an emergency range which includes maximum certified takeoff weight. Regulated landing weight, RLW. The RLW is the maximum weight at which a normal landing is permitted, governed by specific airfield altitude and temperature conditions, bearing strength, landing distance available, and climb requirements such as go-around, approach, or landing climb. VREF is the landing reference speed for the aircraft weight and flap setting, including abnormal landing flap settings. It is 1.3 times the stalling speed for the flap setting. This is VREF equals 1.3 VS. VREF is the target speed at a height of 50 feet above the landing threshold.